takes a look at more implicit differentiation, this time for a harder problem that we're going to see is helpful to solve with a strategy to make complicated things seem a little bit less complicated. So we're going to look at this implicit equation, the inverse tangent of x plus y equals y squared plus pi over 4, which looks like this. And there are asymptotes over here off to the right. Notice that this is clearly not what we would call a function. It doesn't pass that vertical line test. But that doesn't matter. We can still find the rate of change of y. So in order to do it, we're going to do the same thing we've been doing, which is take the derivative of both sides in respect to x. And that's going to get a little bit complicated on the left-hand side. The derivative of the inverse tangent, which we learned about in a previous lesson, is 1 over x squared plus 1. Of course, the x in this case is the argument of the inverse tangent, which is the expression x plus y. So the derivative of inverse tangent is 1 over the inside function squared plus 1, but because of the chain rule, it's times the derivative of the inside. And that has to equal the derivative of the other side, which is just the power, 2y. But because of the chain rule, again, we need to do times dy dx. And remember, the derivative of pi over 4 is just 0 because pi over 4 is a constant. Now, this whole thing down here, it gets to be a bit much. And it can get in the way if you think, oh, well, we're going to have to distribute by that whole thing. It just gets a little intimidating. So one thing you can do, a great strategy, is when things start to be complicated, you can just define for yourself a dummy variable, which will stand for x plus y squared plus 1. We'll call that u, which means that we can refer to this whole thing as 1 plus dy dx divided by u equals 2y dy dx. Now, u is certainly more complicated, and later on we might have to substitute the whole thing back in, but it's definitely easier to work with if we just call it u. So now I'm looking at this and I say, all right, I'm just going to move the u over to the other side by multiplying both sides by u, 2uy dy dx. And then the step now is to collect the dy dx's, meaning move all of them over to one side, so that way we can factor out the dy dx. 2uy dy dx minus dy dx. So what we've done is subtracted the dy dx from this side onto the other side, and then we have to factor out the dy dx. And so dy dx equals 1 over 2uy minus 1, which if the question was to find dy dx, we would just put the u back in and call it a day. But that's not what this question asked us to do. This question asked us to find the equation of the line tangent to the curve. Maybe we should have spoken about this already. But going back to a couple of weeks ago, whenever you see those directions, tangent to the line, that means we know we are looking for something in point slope form. Y minus some y value. I'm going to call it y1 here for the moment. Earlier in the year we called it f of a, but this isn't a function, so I don't want to use that notation. Equals some slope, which of course is the derivative at the point that we're talking about. I don't really want to use the big fancy notation there for it, and since I can't use prime notation because it's not a function, I'll just call it m times x minus x1. Now, we're told to find it at the point 1, 0. So I can plug those numbers in. The y1 is 0, still don't know the slope yet, and the x value we're looking at is 1. So make sure we take a look at what we're doing before we try and do it. We need to now find the slope. What is the slope right here, which is the slope of our curve at the coordinate 1, 0. Well, of course, that would be, in order to find that, we would need to use dy dx evaluated at the point 1, 0. There are a couple of different ways you can write this. I'm going to write x comma y equals 1 comma 0. You could write x equals 1, y equals 0. You can get away with it if you just wrote the coordinate 1 comma 0. I'm just trying to be as clear as possible. And what happens is when we plug in the point 1 comma 0, because of this y right here, it doesn't even matter what u is. I'm going to multiply it by 0 because that's the y coordinate. So while if I were just finding dy dx at any other point, I would need to, kind of plug this whole thing back in there. I don't need to worry about that. In this case, all I have to do is 1 over 2 times u, which I don't know but don't care about because I'm about to multiply it by 0, which just ends up 1 over 0 minus 1, which is negative 1. So our tangent line is just y equals negative 1 times x minus 1. And we can verify that on Desmos by graphing the line. Zoom in a little bit here. Graphing the line, y equals negative 1 times x minus 1. And that certainly appears to be tangent at the coordinate 1 comma 0, just like we wanted it.